Why stability is the most dangerous illusion in science. Stability feels comforting, reassuring, and trustworthy, the kind of concept scientists, engineers, and entire civilizations build their confidence around without hesitation. When something remains unchanged over time, we assume it is safe, controlled, and fully understood. But in chemistry, stability is rarely a permanent state. It is a pause, and pauses are often mistaken for endings. To understand why stability can become dangerous, we need to rethink what it actually represents in scientific systems. Stability does not mean nothing is happening. It means opposing reactions are temporarily balanced. Energy is still moving. Bonds are still vibrating. Molecules are still exchanging information with their environment. The system looks calm only because change is evenly distributed. Modern science depends heavily on this illusion. Materials are certified stable. Reactions are labeled complete. Compounds are approved because they do not change under standard conditions. Those standards become assumptions. Those assumptions become infrastructure, and infrastructure resists questioning once it works. At first, stability delivers everything promised. Structures hold. Reactions behave. Processes repeat flawlessly. Data aligns with prediction. The system feels mastered. This is the first narrative beat, a moment where control appears absolute and uncertainty feels eliminated. But chemistry never stops responding to its surroundings. Temperature fluctuates, pressure cycles, trace contaminants appear, radiation, light, and time apply constant influence. None of these forces are dramatic alone. Together, they reshape probability, and probability is where stability begins to erode. This is the second beat. Stability masks slow drift. A reaction that does not change visibly may still be moving microscopically. Bonds stretch slightly further each cycle. Byproducts accumulate just below detection. Energy redistributes unevenly. Nothing fails. Nothing alerts. And that silence becomes trust. The third beat forms quietly. As trust grows, margins shrink. Systems are pushed closer to limits because they appear reliable. Safety buffers are reduced. Efficiency increases. The stable system is asked to do more, faster, and longer. Chemistry does not object. It adapts. But adaptation is not endorsement. This is where the story begins to tighten. Because stability is most dangerous when it hides how close a system is to transition. When change finally arrives, it does not announce itself gradually. It arrives as sudden reorganization. A reaction shifts. A material transforms. A system behaves differently overnight. Stability was never a guarantee. It was a temporary alignment of forces. And chemistry always remembers how easily that alignment can be undone as systems remain stable for long periods. Chemistry quietly rewrites how risk is perceived because repetition without failure trains humans to confuse endurance with permanence, even though those two ideas are fundamentally different. The longer a system behaves as expected, the more invisible its internal motion becomes, and the more confidently people assume that nothing meaningful is happening beneath the surface. Stability begins to feel like proof instead of coincidence. This is where the illusion deepens. Stable systems are rarely inactive. They are active systems in equilibrium, where opposing reactions cancel each other just enough to maintain appearance. Energy still flows. Molecules still vibrate. Minor reactions still occur and reverse. But because outcomes look unchanged, attention drifts elsewhere. Chemistry continues working without witnesses. Over time, this creates a dangerous pattern. Stability invites optimization. If something has not failed, it must have excess capacity. Margins are trimmed. Loads increase. Conditions are pushed closer to theoretical limits. The system is asked to perform not just reliably, but efficiently, continuously, and without interruption. Each adjustment feels rational. Each one removes tolerance. This is a continuation of the reveal. Stable reactions begin operating closer to transition points. Materials sit nearer to phase boundaries. Chemical processes rely on narrower windows of temperature, pressure, and purity. The system still holds, but the energy landscape flattens. Small disturbances now have larger effects. Stability becomes conditional rather than inherent. Chemistry responds to this pressure patiently. It does not resist optimization. It accommodates it. Reactions slow in some regions and accelerate in others. Byproducts linger slightly longer. Microstructural changes accumulate quietly. Nothing crosses a threshold yet, but thresholds move closer. This is the early conflict, because stability hides direction. A system can appear unchanged while drifting steadily toward a different state. And because nothing fails, feedback never arrives. There is no signal to stop, no warning to adjust. The system teaches its operators the wrong lesson, that nothing needs attention. What nobody expects is how sudden transitions feel once they begin. When stability finally breaks, it does not unravel gradually. It reorganizes. A reaction pathway shifts dominance. A material changes phase. A feedback loop reverses sign. The system behaves correctly according to chemistry, but incorrectly according to expectation. At this stage, intervention becomes difficult. Controls designed for stability struggle with transition. Sensors calibrated for normal behavior miss abnormal emergence. Human response lags behind chemical response. By the time change is recognized, the system has already moved. This is why stability becomes dangerous, not because it is false, but because it is temporary and convincing. It persuades observers that time is on their side, when chemistry has been using that time to prepare a different outcome entirely. And once stability ends, chemistry does not restore it. It replaces it with a new balance, one that reflects accumulated change, not original intention. This is where the conflict fully emerges, because once stability gives way to transition, chemistry moves faster than systems built to preserve the old state can respond, revealing how fragile long-trusted equilibrium really was. What looked like a sudden failure is actually a delayed reaction, the result of countless small shifts finally aligning into a new dominant pathway. As equilibrium weakens, reactions that were once suppressed begin asserting themselves. Minor side processes gain momentum. Energy that was evenly distributed starts concentrating. Localized changes grow instead of canceling out. The system no longer corrects itself. It amplifies deviation. Chemistry has crossed from balance into reorganization. This buildup feels shocking only because warning signs were invisible. There was no single mistake, no dramatic trigger, just accumulated drift. Bonds that stretched 1% too far. Temperatures that hovered slightly higher for too long. Impurities that were always present but never accounted for. Stability absorbed them until it couldn't. Human response often worsens a transition. Controls tighten. Interventions increase. Systems are forced back toward their original state. But chemistry resists reversal. Pushing harder adds stress. Stress accelerates change. The attempt to preserve stability becomes a catalyst for collapse. This is the emotional peak. Because stability promised safety, it justified risk. It encouraged expansion. And now chemistry reveals that stability was not protecting the system. It was masking its exhaustion. The calm before change was not strength. It was stored in balance. At this stage, systems behave unpredictably. Outputs fluctuate. Materials fail outside expected patterns. Reactions occur under conditions once considered safe. The old rules no longer apply, not because they were wrong, but because the system has moved beyond them. This moment forces a painful realization. Stability did not disappear unexpectedly. It was spent, consumed slowly by optimization, neglect, and time. Chemistry simply enforced the next state once the old one could no longer exist. The question now is no longer how to restore stability. It is how to survive a transition it delayed. Because chemistry always resolves imbalance, and resolution rarely resembles a state that came before. The climax is not collapse. It is recognition. Stability was never the destination. It was a temporary alignment of forces that felt permanent only because change moved slowly. Chemistry did not betray the system. It completed the process stability had been postponing. This is the final insight. Stable systems are not safe systems. They are systems accumulating invisible change. The longer stability holds, the more energy, stress, and imbalance it can store. And when release finally happens, it happens decisively. The resolution is not to fear instability. It is to design for it. Systems that survive long-term do not chase permanent balance. They expect transition. They allow margins. They monitor drift instead of assuming stasis. They build flexibility where chemistry will inevitably demand it. Modern relevance makes this unavoidable. Climate systems, energy grids, materials science, biology, every complex system humans depend on exists far from true equilibrium. Pretending otherwise only delays adaptation. And delayed adaptation is always paved with disruption. Once this perspective shifts, stability stops looking reassuring. It starts looking suspicious. Questions replace confidence. How long has this held? What is changing underneath? Where is the stress going? These questions protect systems far better than blind trust ever could. Why stability is the most dangerous illusion in science is no longer abstract. It is a pattern repeated everywhere chemistry is misunderstood. Stability buys time, nothing more, and chemistry always decides how that time is spent. Sometimes the smallest shift in perspective becomes the beginning of a new future. Why